Hey guys, welcome back to the Peer Dependency with our series on multi-threaded programming and concurrency. And today we have the big one, concurrency versus parallelism. So we're going to look at some analogies first. We're going to compare concurrency to parallelism. We're going to look at how they differ, how they are similar, and we'll talk a little bit about some of the pros and cons of each. Now, when you're doing multi-threaded programming and you're working with concurrent applications, you absolutely must understand the distinction between concurrent and parallel. In most environments and in many applications, concurrency and parallelism actually coexist, so I don't want you guys to think of these as completely mutually exclusive topics, as we'll see. But for now, we're going to start with examples and try to grasp what each of these are, and I encourage you to stick around for the entire video because really, I think the analogy for one without the other, it's a little unclear, but when you see both, you definitely will get the big picture. Understanding concurrency versus parallelism is critically important as a software engineer and or programmer. I work at a big tech company, and I can tell you that we have to deal with concurrency issues all the time. If I had no familiarity with concurrency whatsoever going into this job, I'd probably not be there. I can tell you that enterprise applications very often employ concurrency and or parallelism. So here, most enterprise applications involve some sort of asynchrony that is dealt with using evented architecture like event loops, concurrent multi-threading, parallel execution, etc. I would just say from my personal experience, at least nowadays, I would say the top one, evented architecture and event loops, is probably the most common. But there is also a fast follow-up here with concurrent multi-threading. The point here is that this is really, really common. If you are a professional software engineer, you program for a living, it's very likely that you will deal with asynchrony, and the way you deal with asynchrony is using things like concurrency or parallelism. I think we've established it's really important to understand this stuff. I hope that this is a good takeaway for everyone for this series, but I'm not going to belabor the point. Let's continue. So let's start with concurrency. So I have an example here. My crew and I are building a cabin, but we only have a single hammer. So how are we going to build this cabin? Well, we'll take turns. We'll each take turns hammering until the person hammering gets tired, and then we'll let the next worker take over. So the way this would work is, say my work crew is 5 people. One of us is going to start hammering nails, and then once they get tired, they'll hand the hammer to the next worker and they'll take over, and then they'll get tired and hand the hammer to the next worker and they'll take over, and we'll just kind of cycle like that, and we'll all, take our turns doing a little bit of work on the cabin until it's done. So the crew takes turns hammering for a bit, passing the hammer around, while the other workers rest. So what are some of the attributes of this example? Well, we're doing one task at a time, and we're switching between tasks. There's that term again, context switching. So when I hand the hammer to my coworker, that is context switching. Now, attributes of this, as it pertains to concurrency, are that this switching, it preempts the current task. So we stop what we're doing, we hand the hammer to the next worker, we work on tasks partially. Now you'll notice none of us finish the cabin in one go. We pick up tasks where we left off. Maybe I was working on the front of the cabin and some other worker was working on the back of the cabin. When the hammer comes back around to me, I'll continue where I left off at the front of the cabin, and when the hammer goes to my coworker, he'll pick up where he left off at the back of the cabin. So this is an example, an analogy of concurrency. Let's look at parallelism, and we'll do the same sort of scenario, but we'll have the analogy geared toward parallelism, and then we'll tie this back to computing. So my crew has done really well. Our cabins are excellent. People love them. They buy them. We made some good money, and we were able to purchase some new equipment. And now every worker in the crew has their own hammer. Now we can all work on different parts of the cabin at literally the same time. So instead of passing the hammer around and, one of us working at any given time while the others rest, we can all work on the cabin at the same time. So now our business is just growing exponentially because we're all able to do our work at the same exact time. And really the crux of all of this is that we have this thing where we have new equipment. We each have our own hammer, which will come into play when we tie this back to computing. But let's look at the attributes of parallelism here. So the tasks are executed simultaneously, literally at the same time. The entire work crew, we all have our own hammers, and we are all working on the cabin at the exact same time. Like I pointed out with the hammers, we need resources to do this. So in the example, this was the multiple hammers. In reality, this could be multiple CPU cores, and it typically is. So there's this other thing called Singularism. You've been using it already, especially if you've written a program and not used threads intentionally. You're probably using Singularism. This is one task at a time, and you must finish the current task before moving on to the next, i.e. this is a blocking task. So say you have a function, maybe doing some complex math. Maybe you calculate a Fibonacci number. And the function you call to do that does that entire task until it's computed the number, and the function that calls that function is going to just block and wait until it's done. And this would be an example of Singularism, where you do one task at a time, you must finish that task before moving on to the next. Running that task means you block everything else. And I threw this in here because we have our difference of parallelism versus concurrency, but we also want to kind of anchor this by understanding how those are different from what you typically see, which is singularism. Here's the analogy mapping. So in the examples, we have these workers, and in computing, this would be a thread. We have the hammer, and in computing, this would be resources like the CPU, the memory. And then we have the task handoffs. Remember in concurrency where each worker would hand the hammer to the next. This is context switching. And then finally, we have building the cabin, which is in computing the task. And so what are some downsides of concurrency? And we'll pinpoint and hone in on these since this is what we're really discussing in this series. So context switching can be expensive. Sometimes even more so than a task itself. And we'll get into this later in the series when we talk about when would you want to use concurrency, or rather, when would you want to use threads. There are certainly times where you should not use threads in your program. And I think when you first learn about multi-threading in programming, it sounds wonderful, and you think, why don't we just do everything this way? As we'll find, there are some tasks that are just not well suited to threads. Some of these cases, the context switching is just so expensive that it's more computationally expensive than doing the task itself. And what I mean by that is the switching, the remembering where you left off, the maintaining that context, that state, maintaining those separate stacks. Sometimes that is just more computationally expensive, and it takes longer than if you were to just use singularism and execute this task all in one go in a single thread. Dealing with consistency and shared state between concurrent tasks is an insanely difficult and complex problem. As I've said many times before, we'll have a lot of videos later on in the series when we're ready, where we'll talk about race conditions, and we will talk about these things called mutexes and semaphores. We'll discuss why we need them. We'll look at a lot of problem statements and probably look at some examples of real open source programs out in the wild that could have had these problems were they not using what is called synchronization. But in any case, there are downsides associated with concurrency. There are downsides associated with multi-threading. There are times where it is not the best suited thing for the task. So what are the takeaways here? Concurrency is about dealing with many things at once, while parallelism is about doing many things at once. Concurrency is really about the management of many tasks. We talked about scheduling in a previous video. We saw how, we schedule threads on the CPU, and we really are looking at managing these different tasks that can't run at exactly the same time, but we're able to deal with many things at the same time. And parallelism is about quite literally doing these many things at once. This is kind of the adage that I like to keep in my mind that reminds me what really is the difference between these two. And with that, that's our takeaways for this one. I really hope this helped break down the differences between concurrency and parallelism. Of course, if you guys have any questions or comments, leave them down below. And of course, make sure you like and subscribe because I have tons of awesome content coming for y'all. And with that, thanks. We'll see you next time.